Hi everyone, welcome back. In this video, we're going to take a look at Chapter 9, Section 4, which is on vectors. So we're going to do a quick introduction on vectors and vector operations. Okay, all right, so we're looking at vectors. If you've taken physics, you're probably a bit familiar with vectors. If not, that's okay. We'll start from the beginning. Some of this might be a little bit of review, but it will get a little bit more difficult as we go more in depth with vectors. Vectors are a way to represent not only a number, but also a direction. So a few vocabulary words. When we talk about scalars, a scalar is a number or just magnitude. So some value, like 2 is a scalar. 2 could be like 2 feet. It could be 2 miles, so on. Scalars are just numbers. Scalars are different from vectors, which are both a number and a direction. Number and direction. So a vector would be 2 miles to the northeast, for example. So specifying not only how far you're traveling, but also which direction you're traveling. So that's the basic definition of a vector, just looking at a number, which we call a magnitude, and a direction. Vectors can be represented with, usually we'll use letters like V and U. Sometimes you'll see them bolded, like in textbooks. When I write down vectors, I'll usually put a little arrow on top like that to indicate that we're talking about a vector. When we take a vector and plot it on a graph, a vector can be thought of as starting at the origin and then thinking of a point where we end up with if we were to follow the directions of the vector. So for example, to the right here, if we were to start at 0 and go 4 units up, 4 units directly up the y-axis, then this would be our vector here. And we would draw vectors as an arrow. So we have a line here, and then we have an arrow. The vectors are represented as arrows when we graph them. One note is that vectors are different than rays. So a vector, which we could represent here, a vector has an ending point. We start at one point, and then we end at another point. We stop. A ray, on the other hand, is just a direction. So when we talk about a ray, it's a direction, but we don't have an ending point. Rays are what we talk about when we think of angles, for example. If we're looking at an angle, the 2 sides of the angle are going to be rays. They go on forever, don't have an ending point. Vectors specifically have both a direction and a magnitude. Okay, let's take a look at negative vectors next. If we were to take, let's let this vector be called vector v. Negative v. What negative v means is that we have the same magnitude. So the magnitude doesn't change, but opposite direction. So if we take a negative vector, all we're changing is we're flipping the direction. So for example, negative v, if we wanted to graph that in orange, would be starting at the origin, and then we would be going 4 units, but 4 units in this case down. So flipping across the origin. And it would look like this if we were to graph it. Okay, negative v. All right, so let's start to take a look at vector operations. First, I want to talk about how we write vectors. So before we were representing vectors on a plane, on a coordinate plane, you can also write down vectors just using their 2 components, using their horizontal component and vertical component. And this is called algebraic notation. So when we write down vectors, we use these, the like less than and the greater than symbol, and we put those around them. So kind of like parentheses, but pointed. And then we list the x value first, comma, the y value. So similar to an ordered pair. And again, this is the x is the horizontal component, and y is going to be the vertical component. Okay, so for example, we have 2 vectors below. We have vector v and vector u. Vector v has a horizontal component of 0, vertical component of 3, and we can see that to the right here. U, on the other hand, has a horizontal component of 3 and a vertical component of 0. So just 3, 0. So 2 vectors. I've written them out in algebraic notation. I have also graphed them. Let's talk about operations between these vectors. So when we add vectors, one way to add vectors is what we call adding from tip to tail. So you can think about the tip of the vector as the end of the vector, so where the vector stops, and then you take the tail, which is the beginning of the other vector, and you put the tail where that ending is. And then you travel along the first vector, then along the second vector, and where you end up is going to be the sum of the 2 vectors. So in this case, we have v and u. If we were to start off with just v plus u, then we would start off by going up v. So up v, so we're traveling up v. We get to the tip of v, and then we're going to be taking u, and we're going to place the end, the tail of u, and then starting here, we're going to travel the magnitude and direction of u. So in this case, it's going to be 3 units to the right. Okay, so we travel along v, then along u, and we end up at this point right here. And this is going to be v plus u, which we could call w, for example. And w is going to be the vector starting at the origin and ending at that point. So we start at the origin, and then we draw a line directly to that point, and that is going to be the vector w. So that's equal to w, which in this case, if we wanted to write out w, it would be 3, 3. One thing you might notice is that if we were to change the order of our vectors, if we were to take u plus v, we would still end up at w. In this case, we travel down u, and then we get to the tip of u, and then we travel up 3. In other words, the direction that v is traveling 3 units directly up. So we still end up with w, even if we were to start with the other vector. So it doesn't matter which one you start with. What this tells us is that we have commutative. We have the commutative property for addition for vectors. So adding vectors is commutative. It doesn't matter which order we add them, we'll still end up with the same result. One thing to be careful of is when we learn about new concepts, not everything we learn about is going to be commutative. For example, when you start to learn about matrices, if we were to multiply 2 matrices, and a matrix is kind of like a collection of numbers ordered in a square or a rectangle, when we multiply those, that's not commutative for multiplication. So this might seem obvious, but these types of properties, it's good to know that they are true for these new things we're learning. Okay, next let's take a look at subtracting vectors. So vector subtraction, we're going to treat by thinking about vector subtraction as adding the opposite. So we're still using addition, but we're adding the opposite. In other words, the negative vector. So if we were to have v minus u, another way to write that is going to be v plus negative u. So adding the opposites. This is why it's important that we know how to take the opposite of a vector, which we did at the very beginning of the video. What we would do is we would start with v. So v is 3 units up, ending at 3 units up. And then we would apply negative u. So negative u is still going to be 3 units, but it's going to be to the left. So we have u, and we're moving 3 units to the left. This is negative u that we're adding here. So when we take v and subtract u or add negative u, we end up at this point here. And that is going to be our result of v minus u. V minus u. So we can call that, for example, a. In this case, it's going to be negative 3, 3. Okay, so just adding the opposite. Subtraction is not commutative, which makes sense. That's also true for scalars, for numbers we're working with. If we were to do the opposite, u minus v, that would be u plus negative v, which means we would go u, 3 to the right, and then we would go down 3. And then this vector right here would be u minus v. So obviously they're not the same. It's not commutative. Okay, so subtraction, we can just think of it as adding the opposite, which again is the same magnitude, just the opposite direction. Okay, next up I want to talk about multiplication, but specifically multiplication by a scalar. So a scalar is some number times a vector. When we multiply by a scalar, we have the same direction, so the direction does not change, but we multiply the magnitude. And again, the magnitude is just the distance from the origin or the distance we're traveling. We multiply the magnitude by the scalar. Okay, so whatever number we're multiplying by, that applies to the magnitude. So a quick example, if we had u, which is just 0, 3. So u, 0, 3. Right here, and we were to multiply u by 2 times u, we would end up with 0, 6, because we would start at u. We're going the same direction, directly up, except we're going, instead of going up by 3, we're going up by 3 times 2, which is 6. So 2u is just going to be 0, 6. So same direction, but in this case, twice the magnitude. Another example would be if we had v as 2, 1. So v is going to be 2, 1 right here. Then if we were to multiply v by 3, we would be going in the same direction, but we would be traveling in that direction 3 times the magnitude. So write 2 up 1. That's one way to think about it. And then again, write 2 up 1. And then again, write 2 up 1. So 3 times the magnitude. Our final vector for 3v is going to be here. 3v is 6, 3. So as you can see, we're traveling in the same direction, but multiplying the magnitude by the scalar, which makes sense because 2u, if we think about 2u is the same thing as u plus u, which means we're going to be staying in the same direction. When we travel up u, we add another u, which means we're going in the same direction and we're traveling by a distance of u. If it was 1.5u, we'd be adding u and then 1/2 of u. So same direction, we would add u and then we would add 1/2 of u. And at that point, we would get 0, 4.5. So that's how we multiply by a scalar. Multiplying two vectors is a little bit more complicated, and we'll talk about that later in the unit. And there's a specific name for it that we'll go through. Okay, so a couple more quick notes. When we talk about the magnitude of a vector, you might see it written in this notation. If we have vector v, then the magnitude of that vector is going to be written as v with two sets of kind of like absolute value bars around it. So this is the notation that you might see when it's asking for the magnitude of a vector. And the magnitude, again, is just the distance from the origin, or how far you travel along the vector. You might also see the term position vector. The position vector is the same direction and magnitude of the vector that it's referring to, and magnitude starting at the origin. So a quick example would be if we were to have a vector up here, for example. Say we have a vector here, call that vector v. So as you can see, vector v does not start at the origin. So the position vector of v, position vector in this case of v, would be starting at the origin, and then we would have the same exact direction and magnitude. So in this case, right 3 up 2. So the position vector v would be right here. So same exact direction, same magnitude, just starting at the origin. If the original vector doesn't start at the origin. If it does start at the origin, then it's exactly the same. When we find the magnitude of a vector, we can use its components to find the magnitude, and we can do that pretty easily by just using the Pythagorean theorem. So pretty much just finding the distance of a line, for example. For example, let's say we have a vector w, and let's have w be the orange vector down here. The magnitude of w is just going to be the square root of its x component squared plus its y component squared. So w would be written as just x comma y. In this case specifically, w is 3 comma 2, which means the magnitude is the square root of 3 squared plus 2 squared, which means the magnitude is just square root of 9 plus 4, root 13. Okay, so pretty straightforward, just using the Pythagorean theorem to find the magnitude using the components.